Okay, so students will start a class now. Okay, so welcome to today's class. How's everyone? Everything is going on well. So let us start a class. Okay, we'll start a class now. Okay, so let us start it. Okay, so we'll go with the introduction first. We'll see the introductory part. Okay, after that we'll proceed for the next. First we'll see what? First we'll see introductory part. Okay, very good, very good. So if you focus here, we were at this topic, that is interference. First, we'll revise all the things back again. Okay. I hope that I am audible to all of you properly. But for this, let me first see what's happening on the YouTube. Okay. I have to check it out. It's very, very important. So let us see on the YouTube what is happening there. So it's YouTube Avanti Live 13. Yeah, it's just working there. It's working. Let us start it now, okay, without wasting time. How's everyone? Everyone is good? That's great. Okay. So, first, we'll start with this interference. See, these are the learning objectives or the contents. These are the learning objectives or contents of today's class. Okay. So, first, we'll go with this, that is introduction to interference. First, we'll have our introduction to interference, that what is this interference is. Okay. After we'll understand two different type of sources, that is coherent source. Okay. We'll understand about the incoherent source. That what are the different kind of sources, coherent source and incoherent source. Superposition of light waves. Superposition of light waves, this is our third topic. This is all revision going on. At last, we'll see Young's double slit experiment. We'll understand in depth about Young's double slit experiment. Okay, fine. So let us revise this again. That is introduction to interference. See, we have seen this thing. The phenomenon of one wave interfering with another and the resulting redistribution of energy in the space around the two sources of distribution is called interference of waves. Okay. So you can see this animation here. I have already launched this animation many times before. This is say a source S1. This is say a source S2. Suppose this is switched on. So wavefronts are generated as you can see here. And when S2 is also switched on, the wavefronts are generated. These both wavefronts of the light rays basically overlap and they form a pattern on the screen. This is what? Some pattern. This is some pattern on the screen. This is some pattern on the screen. Next is this pattern on the screen. Okay. Third is this pattern on the screen. Fourth is this pattern on the screen. Okay. So this is what pattern. It shows when the two sources like this are switched on and the overlap, the pattern we get on the screen is interference pattern. Okay. So this is here dark band. This is again here dark band. This is again dark band. This is again here dark band. Okay. So if you focus here, we are having alternate. We're having what? We are having alternate dark and bright bands here. Okay. So this is dark. This is bright. This we have observed in the previous class also. This is dark. This is bright. This is dark. This is bright. Okay. So this is seen so many times. Now let us see the definition again. So definition says like this: the phenomenon of one wave interfering with another and the resulting redistribution of energy in the space around the two sources of distribution is called interference of waves. This is known as what? This is interference of waves. Okay, remember it always. What is this? It is interference of waves. So this interference, if you focus, this interference, if we focus between two or more light waves, if we understand the basic meaning of this interference, it's just what? It's just an addition or superposition process, okay, which results in a new wave pattern. Okay, so let us understand how it looks. Before that, let us see how it will look. This you have already seen, by the way. If you see at the back, if I launch this animation again, you can see it. How cool it is. You know, two different individual wavefronts are being overlapped, and then we get a net structure which is shown on your screen. On the screen, we can see alternate dark and bright bands here. This is right, students, you know? And now let us see the condition to set up, revise this condition again. Now we'll revise the condition again to set up. Now we'll revise the condition again to what? To set up a stable and clear interference pattern. Okay, these two conditions must be met. Let me tell you. To set up a stable and clear interference pattern, students, you must understand two conditions. What are the two conditions here? What are the two conditions? Two conditions which must be met are, I'm showing you on the screen. This is the first condition. The waves should be monochromatic. What does it mean? Monochromatic matlab they should be of single wavelength. Mono matlab single. Single. Okay. Second, the sources must be coherent. Coherent matlab, what do you mean by coherent sources? That also we'll understand now in the next slide. This, yes. So if you focus on the definition of coherent source, students, coherent sources are those sources of light which emit waves, okay, that have one thing must be common, that is having the same constant frequency. The more precise word is the same. And those sources of light which are like emitted waves which are having the same frequency must also have in between them zero or constant phase difference. So phase difference between them must also be constant. Okay, this is what, this is coherent light, and this is a source of light. So light rays are going like this. You can see these are very symmetrical, isn't it? These light rays are very symmetrical. Incoherent is what? What is incoherent? Incoherent, if you understand, these are sources, means a source that emit waves having random frequencies and phase differences. Okay. Random frequencies matlab phi 1, matlab phi 2, matlab phi 3, like this. Okay. And phase differences. So the picture which we can predict must look like this. See this. You can see here. See, these are the light rays like in disco, isn't it? We can take the example, but that lights are also coherent. Okay, so you can understand, like, this something like ribbons are in the air. Okay, so this is suppose a source of light, and the light rays which are being showed here, like these are the emitted waves, they are not symmetric. There is a very much random phase difference. If this particle at a particular time position is on the top, some will be at the mean position, some would be somewhat between top and mean positions, है ना? So we'll say these are very different conditions. So we'll comment on this incoherent sources that the phase. Okay, so one of the students have joined. That's very good. Chinvi Chitra Durga students, very welcome to today's class. Okay, I was I was worried that no one have joined, but that's good you have joined. Excellent. Mute yourself. Mute yourself. Chitra Chitra Durga, please mute yourself. Okay. So these are incoherent light sources. Now, see, Chitradurga students, this is the revision going on. Okay, so soon we'll reach to our final slide, which on the previous, I think on the 2nd March where we left. So this you have already seen, but for the revision, like watch it carefully again. Suppose this is a lamp source. This is a lamp source. Okay, and the rays are coming out of it. This is what? This is a slit here. Okay. So light rays are coming out of this, and on the other side there is what? A wavelength filter. This is a wavelength filter. Fine. And you can understand it if the light rays is coming from it. Now, one thing to understand is this. Here, this is incoherent source. Incoherent matlab, what is incoherent? Again, definition. Having the random frequencies and phase differences. Okay. But here it's coherent. Coherent matlab, you know it. Constant frequency and phase difference. That was all the things constant here. Okay. Frequency and phase difference is constant in coherent source. So you can understand from this, the light waves are going like this. Okay. This is light waves going. Light waves, boom, 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 boom. So what is happening in the first side? This gets converted into coherent. Understand this. This light on the hold on. This light of the lampstand is actually what? Polychromatic. It's polychromatic. Polychromatic. This is polychromatic. What happens is light waves when pass through this slit, it becomes specially coherent. Okay, it becomes we'll say still the light is polychromatic, but it's coherent. Okay, and at the last it becomes what? It becomes monochromatic, which is our final goal which we want to achieve. It is monochromatic plus what? Coherent. This is monochromatic plus what? Coherent. Okay. So this question, students, in front of you. This we have seen in the previous class. Chitradurga students, you can reply in the chat box if you're comfortable. Otherwise, I'll be proceeding continuously. Okay. I hope you understand. So there are here you can see it's 4 independent waves are represented by the equations on your screen. This is the first wave given by y1 equals to a1 sine omega t. This is the second wave given by y2 equals to a1 sine 2 omega t. This is the third wave given by y3 equals to a1 sine omega 1 t. This is the fourth wave given equals to a1 sine omega t plus 5. So interference pattern is visible of all at all the times for which pair of waves? Tell the answer. It's 1 2 1 3 2 3 1 4 or 3. Okay, so only these options are given. So we have seen in the previous class that what we did actually, we made a table. Okay, so this is a table. And we use the 4 equations. If equation first, equation third, equation first, equation 4, equation 2, equation 3, equation 3, equation 4. We used all the things, all the values here. Okay. And finally, then we compared the phase differences. Phase differences were compared by this formula, mod of phi 2 minus phi 1, something like this. Okay. And then we have found it. The phase difference is this and this. It means del, it means this, it means this. Okay. So if we focus in all of these values of phase difference between different pair of waves, vibrations given here, so we can conclude like this. This del is time independent. What do you mean by del equals to time independent? Time independent का मतलब क्या हुआ? Del is time independent. What does it mean? It means not function of time. It means not variable. It means basically the most precise meaning of this is, it means basically del is constant. And that is our requirement. No, we must find such a pair of wave equations or vibrations which are having constant phase difference between them. Frequency here given is constant. You can see it yourself, omega, omega, omega. These all the things are constant. But the next condition for the stable interference pattern was this: the phase difference between them must be constant here. Okay. Yeah, so this is achieved. So now let us see the theory of interference of waves. What is the theory? You can understand this is first vibration here. Y1 equals to A cos omega t. This is A, okay. Second equation is this, Y2 equals to A cos omega t plus phi. This is Y1, this is Y2. So theory of interference, the basic theory, it says same as we have explained, as we've learned here now. It says like this: if the two vibrations are superimposed, this is A cos omega t, this is A cos omega t plus phi. If these two vibrations are superimposed, we get the net vibration given by this, that is Y equals to Y1 plus Y2. Always remember this thing. Okay. So even by picture, you can understand that this is a red wave having a less amplitude, and this is a wave which is having somewhat more amplitude. You can understand like this, that the points which are being superimposed are somewhat near. Crest is somewhat near to the crest only. I mean, they are being superimposed symmetrically on each other, kind of. So that's why we get a greater amplitude. Okay. Now let us see some equations. Suppose this is the first equation of that vibration of the wave. Okay. So actually we can't say it is a wave equation. For the wave equation, it must look like this. How the wave equation look? Okay, some one more student have joined. JNVRR. Very good JNVRR students. I haven't seen, I just seen now. JNVRR students have joined that school. Okay. So actually the wave must look like this. That is A cos, or somewhere you'll find sine omega t minus kx. If the wave pulse is moving in this direction. Okay. But here I'll call it's just a vibration equation given for a particular point on the wave, like an SHM vibration. Okay. Suppose suppose the waves are interfering at a point. So at a point, we'll say the maximum vibration which is being formed is given by this. That is y equals to, this is interference. Okay. Y equals to y1 plus y2. And we know this thing, y1 is equals to what? A cos omega t. And y2 equals to what? Y2 equals to A cos omega t plus phi. Remember it. Now, if you take this A common, as I've told in the previous class, if you take this A common from both of this, you'll get in the bracket like this, cos omega t, which I'm putting here with C, and cos omega t plus phi. And the bracket it's A. Okay, complete. So you can use the CD formula in the bracket and multiply that with A. Finally, you will get this answer. That is this much. Okay, I'm erasing it. Hold on. Finally, you will get this answer, which is on your screen. So this says y equals to 2a cos phi by 2. Okay. Y equals to 2a cos phi by 2 multiplied by cos omega t plus phi by 2. Okay. So here if you see, this capital A amplitude is equals to 2a cos phi by 2, where capital A is the amplitude, where A here is known as resultant amplitude. A is what? It's known as resultant amplitude here. Okay. This is y equals to A cos omega t plus phi by 2, where capital A is 2a cos phi by 2. Okay. It's what? Net amplitude. Got it? So this equation which we are seeing is the equation of interference. Now let us use this equation to find the condition of constructive interference. I told in the previous class, maybe, when I say constructive, remember this thing, constructive means maximum. Matlab be optimistic, be positive. Matlab maximum, we have to found the result, we have to take out the output as maximum. Or you can say the brightness will be there, or the bright bands will appear on the screen. Intensity will be max. So these all terms are being connected with this, that is constructive interference. Remember, for constructive interference, intensity should be maximum. This also you must remember. Intensity maximum hona chahiye. We know basically intensity is proportional to amplitude square. And amplitude from the previous equation, students, we have found it at is equals to, any doubt? See, Chitra Durga students and Jinvi are our students. If you're facing any doubt, you can reply in the chat box. This is equals to 2a cos phi by 2. See, intensity is proportional to 4 square cos square phi by 2. This is intensity, I equals to I naught cos square phi by 2, okay? Where I naught here is given by this. So this you got some constant put it, because I have to remove this sign of constant proportionality, no? So I have to put here some constant. 4k a square. This I naught is equals to 4a square k. Okay. And this is known as maximum intensity here. Okay. Fine. Intensity will be maximum. This is given by cos square phi by 2 equals to 1. So I equals to I naught. I equals to I naught. So students, now if I want to give this maximum intensity, I mean what? Cos square phi by 2 must be 1. That will give you I equals to I naught. Okay. So if you find some angles, students, I hope you understand. If you find some angles, given what angles, the cos square phi by 2 must be 1. We know if cos square phi by 2 is equals to 1, okay? So cos phi by 2 will be was also what? Maximum, that is 1 here. Okay. So for cos phi by 2 to be 1, what we'll say? We say these must be the values. Okay. So from here we get the angles, that is, these are the angles. These are the angles in front of you, okay? So we say here, the path difference becomes here N lambda, okay? Because we know this thing K delta X equals to phi. If phi is suppose this 2 and pi for the maximum condition or the constructive interference, we'll say K is equals to 2 pi by lambda. Delta X from this will come out to be equals to N lambda, okay? Remember this, for constructive interference, there is a phase difference 0 between the two waves. Path difference is 0 between the two waves. For destructive interference, now let us see the condition fast. We have already derived all the formulas. But for destructive interference, remember, intensity should be 0. For this is cos square phi by 2 will be 0. And we'll get these angles. Okay, so this is a general angle. This is a general angle phi 2n1 plus 2n plus 1 pi, which will give you cos to be 0. Okay. So from here, the path difference becomes what? K. Actually, it's K delta X equals to phi. K here is 2 pi by lambda. Path difference is delta X. This is 2n1 plus pi here. Okay. So from here, we get the path difference equals to, what's the path difference will be? Here, if you see, the path difference comes out to be this. Remember the values. So students, it's not a rocket science. Okay, one student have more joined. Okay, Janvi, I don't know what's your name. It's Janvi written here. Welcome. So understand here, we are having now two conditions. Remember it always. Okay. What are the two conditions? The first condition is this. The first condition is this. This is what? Just a interference wave. It's not a condition, by the way, it's a general interference wave equation. Next is this, that is, you're fine. Constructive interference, okay. Yeah. So we say for constructive interference, path difference is equals to n lambda. For constructive interference, I will say the path difference is equals to n lambda, okay. And for destructive interference, I will say like this, the path difference is equals to 2n1 plus lambda by 2. What is this? 2n1 plus lambda by 2. And if we see the graph here, it's of course, it's sure that for destructive, whenever we talk about the destructive interference, we have seen the mathematical equations. But now let us see this thing. Whenever I'll call for the destructive interference, destructive matlab destruction, matlab minimum, matlab tends to zero. So for this, I will say crest must overlap with trough. That is, if plus 1 adds with minus 1, it will give you 0. Or suppose some vector is like this 2 Newton up, and if apply at a point other next force, that is 2 Newton down, so this will give you 0 value. Okay, so amplitude goes here to be 0, which you can see on your screen. Interference of waves. See, we have seen this pattern already when from the two sources, mark anyone S1, S2. Suppose this is S1, S2. The waves are interfering. This will give you a pattern, a band on the screen, a dark, alternate dark and bright band, alternate dark and bright band, alternate dark and bright band. This pattern will be observed on the screen. Okay. Remember that this pattern will be observed on the screen. So this you must understand. Okay. This complete process is what basically interference only, no? This complete process is what? It's interference. Now let us see this experiment, that is Young's double slit experiment. What is this experiment? Is Young's double slit experiment. Suppose you're having a source of light. This is what? A source of light. And this is suppose a cardboard which contains in it a narrow slit, a small slit gap. This is what? A small slit gap. Okay. And from this source of light, the light rays are coming out, suppose like this. Okay. So when it will pass through the slit, next to the slit at a particular gap, there are two slits here. These are double slits. Okay. The two gaps are here. Okay. And when the light rays will pass from this, what's going to happen? You are able to observe a band of alternate dark and bright bands on the screen. Slit size here is in the order of the wavelength of light. Remember it. Okay. Now you see here carefully. Now let us see the conditions of this Young's double slit experiment. Okay, first of all, text me any doubt, you students. As anybody having a doubt in this previous slide, I'm launching back. Previous slide means anybody is having any doubt. See this. The experiment is Young's double slit. It's very much familiar to the interference experiment. The bands are symmetric. Center will be maximum, and there will be alternate dark and bright bands. But now we'll derive the mathematical equations for this, as we have derived for the interference pattern. Please reply in the chat box if you're having any doubt. Okay. Please reply in the chat box if you're having any doubt on this. Hello, students. Please reply in the chat box if there is no doubt. Okay. Okay. Write this condition. I will explain you now. Hold on. Okay. So the first write this thing. Through this will derive the equation, through which we'll understand the position of the maximas and position of the dark bands with a particular fixed value. Based on this, we'll solve the numericals. Please understand properly. So make proper notes. Write this note down. Okay. I'll explain you in a minute. Write it down. Okay. So understand it. If you're not having any doubt, I have given you enough time to note it down. So let us see this now. Okay. Okay. So see, suppose this we are understanding the mathematical equations. You can say the mathematics of Young's double slit. Through this, what we are understanding, we're going to understand the mathematics of Young's double slit experiment. Double slit experiment. Okay. Take it. Suppose students, you are having a source here. This is what? S source. This is slit S1. Slit matlab a gap. Okay. This is slit S2, second gap, a small, very less. And suppose between these two slit, the distance is not a gap, but between the two gaps, between the two mini gaps, there is a distance small d. Okay. Suppose the source of light enters here. Okay. So when it will pass through the slit S1, it will go there, and the light from the slit S2 will go there. Okay. So it will interfere here. Okay. So you can see on the screen, the patterns will be formed. Okay. And the slit is basically at capital D distance. So if you focus here on the path difference, the path difference will be how much? See this. If you put a perpendicular here, the path difference between these two waves, that is S1P and S2P, will be equals to, this will be equals to this much. Okay. And if you solve it, students, you will get the value equals to D sine theta, where theta is this angle. Remember it. Okay. Here some mathematics is there. No need to get involved in this a lot. You will do some plus minus mathematics. Okay. And you'll use this theorem, that is hypotenuse square is equals to perpendicular square is equals to base square. And through this, you'll find the hypotenuse, which will be basically either S1P and S2P. Okay. Not equal to, but I can say not equal to. I must remove it. You'll use the, I'm just telling you the overview of the mathematics. Okay. So you'll use the mathematics of this hypotenuse square, base square, perpendicular sum, all these things. Through this, you will find the hypotenuse, which will be looking like S1P. In this order, if you put a root here, this will be like this. Similarly, you'll find some other triangle S1O1P. In that, you will use this parallel, this theorem of hypotenuse square equals to perpendicular square equals to base square. Then you'll get S1P. I must put root here. And then you will take some approximations. Ultimately, you'll get the path difference is equals to, with the approximation, you'll get it equals to how much? That is, you get the path difference like this, and ultimate value will get equals to D sin theta, which you will put as V by D. Hai na? So our main motto is this, to find the path difference completely. Okay. So here I'm getting the path difference, which is equals to V D by D. So from this, students, now what is the use of this formula? Remember, now we know for bright C, this is all for the Young's double slit. As we have seen in the interference, Young's double slit में भी तो screen पे interference pattern form होता है ना. So we'll use this. Okay. You must know this thing, that the position for the bright fringes, for a bright fringe at P, we know this is the path difference formula. You have to keep this equals to n lambda y for the bright fringes. Okay. N0, 1, 2, 3 are for what? This equals to yn and capital D lambda by D. Okay. Okay, let us put this formula back in this. Hai na? If the path difference here is equals to n lambda, this will give the bright fringe. Okay. Y D by D. So y you will get here equals to n d lambda by D. Okay. And will be 0, 1, 2, 3. It will be extending. So depending on this is the y values. Y equals to 0, y equals to d lambda by d, y equals to d lambda by d. Okay. So these are basically corresponding positions. See, corresponding to each of this path difference, there will be y positions. Okay. Suppose this is a screen. So if you start from the center, this y note is basically for the starting positions or reference. It is bright. Then if I go at y equals to 1, which is at a gap of d lambda by d, this is also bright. Then if some more gap, if I go at y2, it's 2d lambda by d. This is also bright. And between these brights, there are dark here. Okay, so this alternate dark and bright bands have been formed here. If we see here in the next, this is, I must remove some of the parts from this. If we see at the next position of dark bands, if I talk about, similarly, we'll use the path difference equals to 2n1 plus lambda by 2 and compare with this the equation which we have just founded. That is Vy small d upon capital D. Y small d upon capital D. So path difference which we are having here equals to this. Y small d, capital D. And this has been compared to what? 2n1 plus lambda by 2. From this, we'll get students different y values. Just see here carefully again. If you see it again, you'll get different y values. Now, can anybody guess what this y values will give? Students, this y values will give you different positions of minimum. Okay. These positions will give you different positions of minimum. Okay. Expression 4. Expression for bright fringe width students. So see, let us understand a little bit, then we'll end the class. 5 minutes just more. I'll take you just 5 minutes, okay? So we'll see the expression for bright fringe width. Bright fringe width means what? First, let us understand this fringe width. See, suppose if you go from, say, if you take a distance yn up to the bright fringe, and then a distance yn minus 1, just this dark pen ending. So this, if you minus this both, if you minus y dash n minus y dash n minus 1, you will get the width of this bright band here. Okay. Which is given by beta here, if you see carefully. That is, beta is nothing but a difference in the position of the nth and n minus 1 to dark fringe. This is the fringe width. And now we want the brighter one. So we can find it out easily by the formula, this one. See, this will be same for both dark and bright. When you will use the formula, no. Okay, let us use the formula of that. N minus 1 for the brighter, for that bright fringe, okay, location. If you see the bright fringe location, the formula is n capital D lambda by small d. So let us use this. Dekho, this formula is for positions of dark fringes. We're getting the fringe width to be what? This much. Now let us use this n minus n into n and n minus 1 in the formula of brighter fringe. Okay. So we'll get these values, that is yn minus yn minus 1. Yn is equals to what? N capital D lambda by small d minus n minus 1 capital D lambda by small d. Okay. So when you will solve this thing again, you'll get the answer as d lambda by d, which you can mark as beta. See now, this is the formula for the position of brighter fringes. So fringe width, the gap between n and n minus 1 in both the cases, either the formula is for the position of dark fringes, either the formula is for the position of the brighter fringes. The distance, the gap between both of these are coming as equals to capital D lambda by small d. What it is coming? Capital D lambda by small d. Capital D is what? Distance of separation of the screen. Distance of separation of the screen from source. Small d is what? Small d kitna hai? Distance between slit. Okay. See, as the separation D between the two slits decreases, fringe width increases. What is it? See, if this D is increasing, fringe width is, if that separation, see, D is decreasing, you can see the formula, no? Fringe width is given by what? Fringe width is what? Basically between n and n minus 1. This much gap is fringe width. Okay. Whether of the dark or either of the bright, the gap will be same. This is the uniqueness of this Young's double slit experiment, theoretically. Experimentally, practically, you may find the changes in the intensities also and the gaps also. So this is d lambda by d. It means fringe width. Remember this formula always. Fringe width is inversely proportional to distance between the slits. Okay. And fringe width is directly proportional to distance of the screen from the sources. So if now the question are being asked from you, you can answer it. That is, suppose I'm launching this. See here carefully. Suppose if someone is asking from you this thing, fringe width, all 4 options are given. They say like this: fringe width, first option, proportional to distance between the screen, distance between the and the source. Second, it's proportional to 1 upon d or inversely proportional to small d, that is the distance between the slits. And 3, 4 options are there. So if MSQs is there, multiple select questions are there, you have to select these two. I hope it's clear. Okay. I hope this thing is clear. So students, in the next class, see again, dark fringe expression, if you see, it's same, hai na? So in the next class, yeah, let's let a little bit see this thing, distribution of intensities. Remember, in the Young's double slit experiment, if there is no any declination or diminution of this thing, that is intensity is same everywhere. All the bright fringes have the same intensity, all the dark fringes have zero intensity. Okay, fine. These are dark fringes. These are bright fringes. See, two slits in the Young's double slit experiment are illuminated by two different lamps emitting light of same wavelength. Okay, will you observe the interference pattern? Okay, understand this. The answer is no. What's the reason? The light waves emitted by two different lamps cannot be coherent. Okay, if they are not coherent, the conditions are what? Coherent hona chahiye. Coherent matlab basically fixed frequency and fixed phase difference. Remember this, okay? Fine. Yes. So students, next we'll see in the, I mean, maybe the day after tomorrow's class. Okay. So here I'm going to end the class. If anybody is feeling it out, facing it out, please reply in the chat box. Finish. Here I'm ending it. Please, if anybody is facing it out, please reply in the chat box. Here it's ended. If anybody want to, like, reply in the chat box, please reply. Any doubts? Okay. Any doubts, students? No? Okay, so students, bye bye everyone. Take care. We'll meet in the next class. Till then, study well. For reference, you can use HCV, I told you again and again, and some modules. So you can text me on this number 861-999-7387 if you need some material. I will send you the PDF soft copy of the modules of I'm having many of the materials of physics. If anybody want to solve LL material, LN, Kota, it's a Premier Institute. So you can solve its modules. I'm having it. Avanti modules also. I'm having Avanti modules also. Resonance also. HCV soft copy also. Whatever the material you just demand, I'll send you on this number. Okay, on the WhatsApp. Write this number. But the thing is this, I'm having all the soft copies only. Okay, I will not send the hard copies. It will not be like courier. So all the things will be sent to you on the WhatsApp PDF. But anything whichever you demand of the physics subject. Okay. So till then, bye bye everyone. Study well, be happy, and we'll meet in the next class. Bye bye students. I'm ending the class. Live streaming, I'm stopping. Bye bye all the YouTube students. Take care. Okay.